Okay, here we go. So today we want to rotate things around the y-axis. And so I look at this first graph. And what I'm going to do is I'm going to look at this area bounded between y equals x squared, x equals 0. So x equals 0 is the y-axis, and the line y equals 4. So that's the x squared piece. This is the x equals 0, and this is the y equals 4. So that's the area that we have, and we're going to revolve that not around the x-axis. If we were going to revolve it around the x-axis, you could see you would get a space in the middle, wouldn't you? We're going to revolve it around the y-axis. We're not ready for that space in the middle yet. So as we revolve this around the y-axis, we get that. And as I select a rectangle that I then choose to revolve, you see I take a slice out of the middle, say like a, I don't know, pineapple or something. I don't know. A ham? Okay. So my slice looks something like this. I have a disc. A for the day, what's the thickness of that disc? dy, as opposed to dx. As soon as you identify that you have a thickness of dy, you are then committed to setting up a problem with y's as your variables. So our bounds will be y values, and our variables will be y. What makes the center? X equals 0. And what makes the outside? Y equals x squared. Uh-oh, that's an x. So I need to change it to y. So therefore I have the square root of y is equal to x. So now you can see the radius, can't you? So the volume of this disk is pi times r squared dy. That's the volume of this disk. So therefore, I don't just want one disk, I want an infinite number. So pi times y dy. And instead of looking for x values as your bounds, I'm looking for y values. So the first y value would be down here, which is 0. And I go up to a y value of 4. Now just note that this intersection point here occurs at 2, 4. And this one occurs at negative 2, 4. So if you did x's, you would go from negative 2 to positive 2, but that wouldn't make any sense. Okay, we're stacking them from down here to up here. So therefore we have 4 as our y value. Make sense? Yes. So I have the picture, I have my organizer, I have my integral. Evaluating it, we all know, is not very difficult. So we take the antiderivative, which is y squared over 2, evaluate it at 4 and at 0, and as Katie said, and others have said, yes, we do get 8 pi. Basically identical to what we did yesterday, wasn't it? We did the square root of x yesterday. So you see how you maybe have to switch it, solve for 1. Okay. So we're not going to do 7. There's really not a whole lot of point to 7. So I'm just going to put a line through. And this one takes a lot of space. So we'll take some time here to solve this one. So I'm going to draw the picture. So find the volume of the area between y equals x cubed. I'm going to draw x cubed. And x plus y is equal to 2. X plus y equals 2. Still in calculus, some people get to this and they don't know what to do with it. Don't put it into slope-intercept form. Just as an x-intercept of 2 and as a y-intercept of 2. You make one of them 0 and solve for the other, right? So 2, 2. So the easiest way to graph this is just go 2, 2. So skill we teach to our 8th graders. So, and finally, it says x equals 0, which is this portion right here. Can you see the shaded region? It's right here, okay? And as I rotate that around, so I make the exact same shape, right here, yep. I want to find this volume. Do you see the issue as I slice it? So I slice it here. Thank you. So what Katie points out is that as I slice this, what serves as the outside or the radius of my disc is the line. Whereas if I slice it here, the outside of my disc is the cubic. Nope, top bottom will not work because yes, when you have a change in the radius from one function to another, all we can really do in this situation is set up two integrals. And we will break it right here. Now, we could do the algebra and solve for what that intersection point is, or sometimes it's just easier to make a really good guess and check. What do you think is that intersection? 1. So you think that that point is 1, 1? Let's check if that works. 1 equal to 1? Yes. Is 1 plus 1, 2? Yes. So 1, 1 is the intersection point. Sometimes it's just easier to make a good guess and see if it's right. Excellent. We did that. Now, we will set up two integrals. The first one, I will do this disk. Where the center is x equals 0. What is the thickness? dy. What makes the outside of the black one? X plus y equals 2, but it needs to be with the variable y. So therefore it's x equals y, or 2 minus y. Very good. So that has to be, all right. We set up the integral. Pi times my radius, 2 minus y squared dy. What is the lower bound? 1. And the upper bound will be 2. Pi times the integral from 1 to 2 of 4 minus 4y plus y squared dy. So pi times it's like I inadvertently put a second parenthesis in there, sorry. So right here, pi times 8 minus 8 plus 8/3 minus 4 minus 2 plus 1/3. 8's cancel. This makes 2. So I have pi times 8/3 minus 1/3 is 7/3 minus 2 or 6/3, and I get pi over 3. Are we done? No, we did the top portion, now we need to do the bottom. That was in green. So the bottom portion, again, is constructed from x equals 0. And what is the outside? Yep, the y equals x cubed. Uh-oh, I gotta have it in terms of y because its thickness is dy. Cubed root, so, or x equals y to the 1/3, I'll write it. So my integral, what are my bounds? 0 to 1, pi times r squared. What do you get if you square y to the 1/3? Square y to 1/3, you get y to 2/3. Standard derivative of y to the 2/3. Three pi over 5. What do? Add them. Common denominator, 15. So pi over 3, 3 pi over 5 is 5 pi over 15 plus 9 pi over 15, 14 pi over 15. It's a nice problem, isn't it? Before I give you your 2 problems for homework, I would just like to ask you this question. We often wondered why that dy was there, didn't we? Kind of makes sense now, doesn't it? I mean, it is very important. It's used all the time in calculus. I know I had frustrations the first time I saw the dy, and it's hard to explain right away, but when you understand terms of working with area and volume, critical. radius. Oh, wow. Once again. There you go. Page 391, numbers 5 and 6. That's all. You can text your friends from Hawaii and tell them that, so that's all I want you to do today. So the assignment that I gave them, and I changed it because some of those are washer problems that we don't know how to do yet. So you have enough work with these problems. I know what I gave you yesterday were 4 problems, and I know that I gave you the 8 problem worksheet, the area bounded between 2 curves. So this is enough to keep you busy. When we come back for break, we will practice basic area and basic volume. Then we will get into difficult volume.